Welcome to the deep dive. Today we're really getting into the engine room of modern computing.
Yeah, the physical layer of PCI Express.
Exactly, PCIe. We're looking at how they made those huge leaps in speed. You know, Gen 3 at 8 gigatransfers per second, then Gen 4 doubling it to 16, and Gen 5 doubling it again to a crazy 32.
It really is an amazing story of constant engineering push. I mean, PCIe is just fundamental now, isn't it? Graphics cards, NVMe drives, network cards, AI accelerators.
Everything high-speed connects through it.
Right. Then the demand for bandwidth just keeps going up and up. Think AI, data centers, they're hungry.
So the big question we're tackling is how? How did they actually pull off these speed boosts? What had to change deep down at that physical electrical level?
That's the core of it, the PHY layer. That's where the signals actually happen, where the basic structure of the data is defined. It's the real nuts and bolts.
Okay, so we're going to unpack that. We'll look at things like encoding schemes.
Yep.
How the data is represented.
How the data blocks are structured.
Data versus control stuff. Those control mechanisms, like skip-ordered sets.
Crucial for timing.
How they frame the actual packets, deal with timing differences between lanes to skew.
Yeah, that's a big one for multi-lane links.
And even some really specific stuff they added for the later gens, like pre-coding.
Especially for Gen 5.
Our goal here is to give you those aha moments. You understand the core ideas, the breakthroughs, without getting totally swamped in, like, datasheet details.
Absolutely. Make it clear, make it click.
Right. Let's start with probably the most fundamental change, the encoding.
Yeah.
How they represent the data.
Okay. So back in the Gen 1 and Gen 2 days, they used something called 8B10B encoding.
Right. I remember that. 8 bits of data become 10 bits for transmission.
Exactly. And it had good reasons. Those extra 2 bits helped ensure DC balance, meaning you didn't have too many ones or zeros in a row, which is bad for the signal. And it guaranteed enough transitions for the receiver to easily lock onto the clock signal embedded in the data.
Makes sense. Good for signal integrity.
Yeah.
But what was the downside?
The downside was, well, it's right there in the name, 8B10B. That's 2 extra bits for every 8 bits of actual data. That's a 20% overhead.
20%. Wow.
Yeah. So to get, say, an 8 gigabit per second effective data rate, you actually need to run the raw signaling at 10 gigatransfers per second. That inefficiency was a major hurdle for pushing speeds higher. It just cost too much in terms of signal complexity, power.
Okay, yeah, that's a significant bottleneck.
Yeah.
So Gen 3 rolls around, aiming for 8 GTs.
Yeah.
How did they get past that 20% tax?
They made a really smart switch. They moved to 128B, 130B encoding.
Okay, 128B, 130B.
Bigger blocks, much bigger blocks. Instead of 8 bits, they group 128 bits of data together. And instead of adding 25% overhead like 8B10B did, 2 extra bits per 8, they add just a tiny 2-bit header.
2 bits for 128 bits of data.
Yep. That brings the overhead down to just 1.54%. Tiny.
Whoa, okay, that is a massive difference.
It was the key, really. It meant that the 8.0 GT's signaling rate in Gen 3 could deliver almost the full 8 GBPs of usable bandwidth. Huge efficiency gain. And what's interesting is they stuck with this 128B, 130B scheme for Gen 4 and Gen 5 too.
So the later speed increases were more about pushing the raw signaling rate, knowing the encoding was already super efficient.
Exactly. The encoding groundwork laid in Gen 3 directly enabled the scaling for Gen 4 and Gen 5.
Okay, so this little 2-bit sync header sounds really important if it replaced the function of the extra bits in 8B10B. What does it do?
It does 2 critical things. First, it provides a clear marker for the receiver to find the start of each 130-bit block. Synchronization.
Like finding the beginning of a sentence?
Kind of, yeah. And second, the pattern of those 2 bits tells the receiver immediately what kind of block it is. If the bits are 10, it's a data block carrying the actual payload, the TLP or DLLP data.
Okay.
If the bits are 011, it's an ordered set block. And those carry special control information, not user data.
So tiny label, data or control.
Pretty much. And because this sync header is so vital for just basic block lock, it actually isn't scrambled like the data payload is.
Oh, okay.
If the receiver messes up reading that 2-bit header, it knows something's fundamentally wrong with the sync, and the link usually has to go into recovery to reestablish it.
You mentioned scrambling. Is that how 128B, 130B handles the DC balance and clock recovery stuff that 8B10B did more directly?
Spot on. 8B10B had deterministic rules within the 10-bit symbols to guarantee DC balance and transitions. 128B, 130B relies on scrambling for that.
How does that work?
Before the 128 data bits get their 10 sync header attached, they get XR'd with a pseudo-random bit sequence generated by something called a linear feedback shift register, an LFSR.
LFSR, okay.
Yeah, it uses a specific mathematical formula, a polynomial, actually the same one for Gen 3, 4, and 5, to generate this long, seemingly random string of bits. It effectively mixes up the data.
Predictably random, though.
Predictably random, exactly. The receiver has an identical LFSR synchronized to the transmitters. It applies the same pseudo-random sequence via XOR and out-pops the original data, descrambled.
Here's the benefit.
Two main benefits. First, it breaks up long runs of identical bits, long strings of ones or zeros, which, as we said, can mess with clock recovery. Second, it statistically ensures DC balance over time. It won't be perfectly balanced in every single block, but averaged out, it works for the AC-coupled links used in PCIe.
Got it. And you said only data blocks get scrambled.
Right. The ordered set blocks, the ones with the O1 sync header carrying control info, they are not scrambled. They need to be easily recognizable. And the scrambler itself gets reset at specific points, like during link training, to make sure both sides always stay perfectly in sync.
Okay, so we have data blocks, 10 sync, scrambled payload, carrying the main traffic.
Yep, TLPs and DLPs, basically. That's what flows during normal operation, the L0 state.
And ordered set blocks, O1 think, unscrambled, carrying these special control messages. Tell me more about these ordered sets.
They are absolutely crucial. Think of them as an embedded control channel running alongside the data. They handle link training, when two devices first connect and figure out how fast they can talk, how many lanes to use.
Negotiation.
Right. They manage link maintenance, power states like L1 and L2, and really importantly, clock tolerance compensation.
Ah, okay. You mentioned them acting as reliable markers, too.
Yes. Because they have fixed known patterns and aren't scrambled, the receiver can reliably detect them even if the data stream has noise. They help keep everything aligned, especially across multiple lanes. They're like guideposts in the data stream.
So what are some key examples of these ordered sets?
Well, probably the most frequently discussed one is the SKP ordered set. SKP skip.
Skip, what's it skipping?
It's designed to handle clock tolerance. See, the clock on the transmitting device and the clock on the receiving device aren't perfectly identical. The PCIe spec allows them to differ by up to plus or minus 300 parts per million.
Tiny difference, but I guess it adds up.
Exactly. Over millions and billions of bits, that tiny difference means one side might be sending slightly faster or slower than the other is receiving. This can cause the receiver's internal buffer, it's called an elastic buffer, like a small FIFO, to either fill up completely, overflow, or empty out completely, underflow. Either way, you lose data.
Okay, that's bad. How does the SKPOS prevent that?
The transmitter is required to insert a SKPOS into the data stream periodically. For 128B, 130B, it's roughly every 370 to 375 blocks on average.
Right.
The receiver watches for these SKPOS. If its buffer is getting too full, meaning the transmitter is slightly faster, it can just discard a SKP symbol from the incoming stream, effectively slowing things down a tiny bit.
Ah, just throws one away.
Yep. And if the buffer is getting too empty, transmitter is slower, the receiver can insert an extra idle character, essentially a SKP symbol, into the stream it passes upwards.
So it adds one. It's dynamically adjusting the rate.
Precisely. It keeps the buffer levels happy and prevents overflow or underflow due to those small clock differences. Now, here's a neat detail. The transmitter can't just stop mid-packet to send a SKPOS.
Oh, right. It has to finish the current TLP or DLLP.
Exactly. It waits for the packet to end, sends an end marker, and then it can insert the SKPOS if it's due. This means the actual interval between SKPs can vary a bit based on traffic.
But the long-term average holds.
Correct. And the receiver's elastic buffer has to be deep enough to handle those variations.
Clever. And you mentioned different types of SKPOS.
Yeah, there's the standard one just for clock compensation. Its first few bytes identify it as such, but then there's also a control SKPOS.
Control? What's that control?
This was added mainly for a feature called lane margining. It allows software, through the link, to actually tweak the receiver's physical settings like voltages or timing on the fly. The control SKPOS carries the commands for this.
Wow, so they repurposed the clock compensation mechanism to add remote control to the PHY settings.
Pretty much. It's a really efficient way to add that capability without needing a whole separate signaling path. Uses the same basic structure, just puts control data in some of the reserved bytes.
Very cool. What other ordered sets are important?
Well, during link training, the SDS ordered set start of data stream is critical, especially in the configuration state. It helps align the blocks across multiple lanes. It actually carries the lane number and a block sequence number.
So that helps with the skew problem you mentioned earlier.
Exactly. We'll get to skew in a moment, but SDS is key for establishing that initial alignment.
Okay.
Others?
Sure. EIOS electrical idle ordered set. That's sent just before a device drops into a low power state like L1, signals it's going quiet.
Makes sense.
And then EIOS electrical idle exit ordered set, that's the wake-up signal, tells the other side it's coming back online. The exact pattern can vary a bit by generation, like the Gen5 version is slightly different.
And I think I've heard of TS1 and TS2 training sequences. Ah, yes, very important. TS1 and TS2 ordered sets are the real workhorses during the LTSSM, the link training and status state machine. That's the whole process devices go through to negotiate the link speed with equalization settings.
So they carry the negotiation data.
Packed with it. Devices exchange TS1s and TS2s in states like polling, configuration, recovery, advertising their capabilities, and agreeing on parameters. The receiver usually needs to see several identical TS sets in a row to confirm a setting before moving on.
So reliable detection of all these different ordered sets is fundamental to managing the link.
Absolutely. It's like a hidden control language running underneath the main data flow.
Okay, that leads us nicely into the skew issue. You mentioned it a couple of times. What exactly is skew in PCIe, and why is it a problem at these speeds?
Right. So imagine you have a multi-lane link, like a by 4 by 16 graphics card slot. To get that high bandwidth, data is striped across all those lanes simultaneously.
Like parallel highways.
Good analogy. But in the real world, those highways aren't perfectly identical. Tiny differences in the length of the copper traces on the motherboard or the chip package, maybe slight variations in the silicon. It means signals sent at the exact same time from the transmitter might arrive at the receiver at slightly different times.
One car gets there a fraction of a second before the others.
Exactly. That difference in arrival time between lanes is skew. And it's not just static from manufacturing. Dynamic skew gets introduced too.
How?
Remember the SKPOS insertion and deletion for clock compensation? That happens independently on each lane. So one lane might insert a skip while another doesn't, shifting their relative timing.
Okay, yeah.
Starting with Gen4, you also have retimers involved in longer links, and they can introduce skew as well.
So if the data from different lanes arrives out of sync, you can't just stitch it back together, right? It'd be scrambled.
Completely corrupted. You'd fail the CRC checks for sure. The receiver must realign the data from all lanes before it can reassemble the original byte stream. Deskew is non-negotiable.
So how do they achieve this realignment? What's the mechanism?
It's a combination of things. First, remember those elastic buffers we talked about for clock compensation? Each receiver lane has one.
The little FIFOs?
Right. They act as temporary holding pens for the incoming 130-bit blocks from each lane. They provide the buffer space needed to absorb those arrival time differences. The size is chosen based on the maximum expected skew.
Okay, buffers give some slack. What else?
They use the 2-bit sync header. Since each lane detects block boundaries independently using that header, it knows where each 130-bit chunk starts and ends on its specific lane.
So each lane finds its own blocks.
Yep. Then, during link training, remember those SDS ordered sets, the ones with the lane and block numbers?
Yeah.
The receiver uses those to figure out the initial static skew between the lanes. It sees block #N arrive on lane 0 at time t0, on lane 1 at t1, and so on. That gives it a baseline measurement.
Establishes the starting offsets.
Exactly. Then, during normal operation, L0 state, the receiver continuously monitors the alignment. It might look at the fill levels of the elastic buffers or the relative arrival times of sync headers. And here's the clever part. It dynamically adjusts the read pointers for each lane's buffer.
Adjust when it reads the data out.
Right. It can effectively delay reading from the faster lanes just enough so that when it does read the 128-bit payloads from all lanes simultaneously, they all belong to the same original piece of data that was transmitted together.
So it waits for the slowest lane, essentially.
In effect, yes. It aligns everything to the slowest lane's arrival time by buffering the faster ones. This continuous dynamic adjustment handles both the initial static skew and any dynamic skew that crops up later from SKPOS or retimers, ensures data integrity across the lanes.
That sounds incredibly complex, but also very elegant. Okay, so lanes are deskewed. How does the PHY then deal with framing the actual TLPs and DLLPs within this stream of 128B, 130B blocks?
Good question. So the data link layer hands down a stream of bytes representing TLPs and DLLPs. The PHY's job in L0 is to get this stream across the link using 128B, 130B.
Right.
First step, as we discussed, is scrambling the byte stream for data blocks. Then it chops the scrambled stream into 128-bit chunks. Each chunk becomes the payload of a data block and gets the 10-sync header.
But TLPs and DLLPs aren't always exactly 128 bits long, or multiples thereof. They vary, right?
Exactly. That's the tricky part. A single TLP might be huge and span many data blocks. Or you could have a couple of small DLLPs fit inside one data block. The block structure doesn't inherently align with the packet structure.
So how does the receiver know where one packet ends and the next begins within this stream of data block payloads?
They use special framing markers. These are specific control sequences, sometimes called K-codes in the context of the logical layer, that are inserted into the data stream before it gets scrambled.
Ah, inserted before scrambling. There's little flags in the original data.
Precisely. The most important ones are STP start TLP marks the beginning of a transaction layer packet.
Okay.
STP start DLLP marks the beginning of a data link layer packet.
Got it.
And then ND or EDB. ND marks the normal end of a packet. EDB end bad might indicate an error or truncation.
And you mentioned EDS earlier. End data stream.
Yes, EDS is often used right after an ND marker. It can help with alignment or signal that an ordered set, like a SKPOS, is about to be transmitted, effectively pausing the TLP-DLLP stream.
So the receiver processes get the 130-bit block, check the sync header. If it's 10 data block, descramble the 128-bit payload,
Right.
and then scan that descrambled byte stream looking for these STP, SDP, END, EDS markers to figure out the actual packet boundary.
You've got it. That's how it reconstructs the original TLPs and DLLPs to pass back up to its data link layer.
That sounds quite a bit more complex than how 8B10B did it. Didn't it use special K-codes that were distinct from data symbols?
It did. 8B10B had dedicated symbols, K-codes, specifically for marking packet boundaries like STP, END, etc. They were inherently different from the data symbols. This 128B130B method relies more on parsing the descrambled data stream for these embedded markers.
Seems like maybe that complexity was a factor in moving to FLITs and PCIe 6.0, fixed-size packets.
Very likely. FLIT mode in Gen 6 simplifies framing and error handling quite a bit, partly addressing the complexities that arose with 128B130B's in-band framing.
Interesting. Okay, so we've got data encoded, framed to skewed, but it's 16 GTs, Gen 4, and especially 32 GTs, Gen 5. Just keeping the data correct must be a huge challenge. What about data integrity checks at the PHY level itself?
Yes, signal integrity is paramount at those speeds. Noise, interference, tiny things can flip bits. The primary mechanism for detecting errors remains the CRC checks performed at the data link layer.
The LCRC for TLPs and the 16-bit CRC for DLPs.
Exactly. Those are mandatory. If the receiver calculates a different CRC than the one received, it flags an error, sends a NA, negative acknowledgement, and the transmitter replays the packet from its buffer. That's the core error recovery loop. There's also optional end-to-end CRC at the transaction layer for extra protection.
So CRC at the DLL is still the main safety net. But our outline mentioned data parity checking specifically for Gen 4, Gen 5. Is there some kind of additional PHY level parity check happening on the 130-bit blocks themselves?
That's a point that sometimes causes confusion. You might see references to parity checking in PHY discussions or diagrams. However, based on the core PCIe specifications, there isn't a standardized mandatory PHY level parity check applied across the entire 130-bit block that functions like the DLL CRC for error correction via replay. The main mechanism specified for link-level data integrity is definitely the DLL CRC. Now, it's possible that individual chip vendors implement internal parity checks within their PHY silicon for diagnostic purposes, or perhaps there are optional features related to this, but it's not a core, required part of the 128B130B transmission process in the same way as the sync header or scrambling. Sometimes the term parity might also be used loosely when actually referring to the stronger CRC checks.
Okay, so rely on the DLL CRC as the primary check. That clarifies things. But then there's pre-coding, introduced specifically for Gen 5 at 32 GTs. That sounds like a definite PHY level addition for integrity.
Absolutely. Pre-coding is a big one, and it's mandatory for 32 GT's operation. It directly tackles the severe signal integrity problems you face at that speed, especially with NRZ signaling.
Non-return to zero, just high and low voltage levels.
Right. At 32 GTs, sending NRZ signals through typical PCB traces causes a lot of signal loss and distortion. The signal gets smeared out, so the receiver needs very powerful equalization techniques to clean it up and figure out if a 1 or a 0 is sent.
Equalization tries to undo the channel damage.
Exactly. And a key part of that equalization is often a decision feedback equalizer, or DFE.
DFE, what does that do?
It uses the receiver's decisions about previous bits to help cancel out interference affecting the current bit. It's like using the past to predict and remove noise from the present. Very effective.
But there's a catch.
There's a catch. What happens if the DFE makes a mistake on one bit? That wrong decision gets fed back into the equalizer.
And potentially causes errors on the next bits.
Precisely. It's called error propagation. A single bit error can trigger a burst of subsequent errors, and the stronger the DFE you need, like at 32 GTs, the worse this error propagation effect can become.
Okay, so how does pre-coding fix that?
Pre-coding cleverly breaks that error propagation chain. It's a logical operation done at the transmitter before the data is even sent. The transmitter essentially pre-distorts the data in a specific way based on knowledge of the receiver's DFE characteristics, which are figured out during link training.
It anticipates the DFE's behavior.
Kind of, yeah. Then, at the receiver, after the DFE does its work, there's a corresponding decoding step. The combined effect of the transmit precoding and the receive decoding means that even if the DFE makes a single bit error, it's much, much less likely to cascade into multiple errors.
It stops the burst error effect.
That's the goal. It makes the link much more robust against single-bit DFE errors. And as I said, it's mandatory for 32 GTs. If the receiver needs it, which it generally will at that speed, the transmitter must enable it.
Was it used in Gen 3 or Gen 4?
No. The signal integrity challenges at 8 and 16 GTs, while significant, generally didn't require this extra step. DFE alone, or simpler equalization, was sufficient. Precoding really marks that step change in difficulty hitting 32 GTs reliably.
It really shows how the logical and electrical aspects get tightly intertwined at these speeds, doesn't it?
Absolutely. You can't just treat the PHY as a simple pipe anymore. The logic has to actively compensate for the physics.
Wow. Okay, that's an amazing journey through the PHY layer changes. So just to quickly pull it together, the big efficiency win came from 128B, 130B encoding.
Yep. Slashing overhead.
Ordered sets became crucial for control, timing, like with the SKP-OS.
The embedded control channel.
Lane skew became essential for multi-lane links using elastic buffers and dynamic alignment.
Handling those timing differences.
Framing packets within blocks relied on those pre-scrambling markers, like STP and END.
The in-band signposts.
Data integrity still primarily leans on the data link layer CRC.
The main error check and replay mechanism.
And then Gen 5 had to introduce PHY-level precoding to combat DFE error propagation at 32 GTs.
You got it. That sums up the key adaptations really well.
It's just incredible how these layers of innovation built on each other to deliver the bandwidth we rely on today.
It really is. Each generation faced new physics challenges, and engineers found clever ways, often combining electrical and logical tricks, to overcome them.
Truly fascinating stuff, and it really makes you, the listener, think, doesn't it? How these deep fundamental changes at the physical level don't just mean faster downloads, but shape the entire architecture of our systems. Where will the next bottleneck appear? As we keep pushing for more speed, more data, what kind of ingenious hacks at this foundational level will they need to invent next? Definitely something to ponder. Thanks for joining us for this deep dive.